In this video, we'll be doing a little exponential function recap while introducing what a logarithmic function is. And we're going to start off by graphing the exponential function f at x equals 2 to the power of x. Now, if you forget how to graph that, remember you could always do a table of values. So just on the side here, I'll put a small little 1. I like that symmetry, a few negatives, a few positive x's, so just going from -2 to 2. And then 2 to the power of -2 is a quarter, or 0.25. 2 to the power of -1 is a half, or 0.5. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And you know what? I'm just going to add 3 as well. 2 to the power of 3 is 8. So I'm going to go ahead and plot these points. And then connect the dots. Now I know on the right the function is going to increase forever. This is a growth example. And on the left we are always going to stay in the positives. And that's because an exponential has that horizontal asymptote at y equals 0. So I'm actually just going to start my little comparison on the side here. Exponential, and then the logarithmic function. So an exponential function has a horizontal asymptote at y equals 0. And then another nice little feature is that the y-intercept is 0, 1. And it always is for a function in the form b to the power of x. All right, time for the inverse. The inverse, I'm just going to take my table of values and I'm going to interchange the x's and the y's because that's what an inverse is. It's all about swapping x and y. So we'll have 0.25 with -2. I'm going to go ahead and plot that point. 0.5 with -1, 1, 0, 2, 1, 4, 2, and 8, 3. Connect those dots. Now, I can see that to the right, it's going on forever, slowly upwards. To the left, I'm going to stay in the positive x values, because if all of the y values on the exponential are going to be positive, then all of the y's are going to be positive because we're just swapping them, which means a logarithmic, or sorry, we haven't gotten there yet, the inverse function has a vertical asymptote at x equals 0. Okay, now what we've just graphed here, yes, are inverse functions, and the inverse of an exponential function is a logarithmic function. So I'm just going to take this equation, y equals 2 to the x, and the way we find the equation of the inverse is by first swapping x and y. So I'm going to write x equals 2 to the power of y, and then the way we isolate for y here is actually by using logs. Now, the way we convert, this is going to be our first time seeing it, the way we convert between exponential and logarithmic forms is the following. The answer to a logarithm is the exponent. So the y is going to come out front because that was the exponent. Then I'm going to write log. The base of the exponent is going to match the base of the log. And then something that we call the argument is the answer to the exponential. So this x here is called the argument. Okay, so the bases match. I like to see this as a little spiral, if you will. Here's my base, 2 to the power of y equals x. Okay, if you look back and forth between exponential and logarithmic. So the inverse is y equals log base 2 of x. That's how we would communicate that. And now I'm just going to go to my comparison. A horizontal asymptote at y equals 0 was for the exponential, whereas the logarithmic function, which was the inverse, had a vertical asymptote at x equals 0. Then the exponential function had a y-intercept always at 0, 1, but for the logarithmic function, it's going to be an x-intercept at 1, 0. Now, the exponential function was increasing, and so is the logarithmic, so they're going to have the same type of increase or decrease. And let's also compare the domain and range. So the exponential has the domain of negative infinity to infinity, and a range of 0 to infinity because of that asymptote, whereas the logarithmic, its domain is 0 to infinity, and the range is negative infinity to infinity. So they kind of did a swap. Now, this idea that the domain is 0 to infinity is very important. We cannot take the log of a negative number, and that can be seen from this visual. When I took the inverse of the exponential, it forced all of my x's to the right of that y-axis. So, and now because the x is in the argument always has to be positive. That's going to be very important later on when we do solving, simplifying, and restrictions. So just before we finish up this video, I just want to practice converting between exponential and logarithmic form. Okay, so let's say I have y equals log base 5 of x. The exponential form, the bases match, so it's going to be 5, and it's going to be to the power of y equals the argument. Or if I have log base 2 of, oh, that's actually the same example, log base 2 of 16 equals 4, this actually means, here's my base 2, 2 to the power of 4 equals 16. Okay, so here's what I was saying earlier, the answer to the log, so in this case it was 4, the answer to the log is the exponent on that base. Okay, so actually, just a little sneak peek for the next lesson, you'll see this more in the next video, but if I had log base 3 of 9, what this is really asking is 3 to the power of what gives me 9, because the answer to the log is the exponent. So then when I'm thinking, well, I know 3 to the power of 2 is 9, so that means log base 3 of 9 is equal to 2. So practicing the back and forth between logarithmic and exponential form is going to be very important for simplifying logarithmic expressions, and also it's going to be important for solving, both things that you'll be seeing over the next few lessons.